So let's start. So I'm here to talk about what are we doing for Hadoop at Uber, what we did, what are we doing, and what we are willing to do or what we are in for the future. So who am I? I'm senior software engineer at Uber. I'm Mayank Bansal. I'm a Hadoop committer, Uzi PMC. Before I was at eBay working on Hadoop, and then before that I was in Yahoo and working on Uzi. The agenda of the talk is pretty simple. I'll talk about the past, the challenges, what are we doing and what we did along the way, and where we are heading, right? That's more important. So Uber missions is very small, which is make transportation as reliable as running water everywhere for everyone. We are right now on 75 plus countries, 500 plus cities, and we are growing as we speak. So let's talk about how Uber works, right? So you take out your phone, open the app, and you probably go put a destination where you want to go. Then some car will show up. In this case, it's probably a self-driving car. And then you sit in the car and you go. So the point of this is each and every point, all these interactions is pretty much driven by the data. So when you say I want to when you open the app, there are a lot of data computation happens. Where is this a fraudulent user? Where he wants to go? What is the GPS locations? When you set the address, then what is the best way or best possible route you should go with? When the car shows up, which car, which driver, what is the proximity? Is this a Uber pool? What is the best way we can combine multiple riders together? And when you go, then we charge your cards, credit card, and there are a lot of other receipts generation, and there are a lot of other data activity happens. So pretty much whatever we do in the whole interaction with the rider and the driver partners it's a data-driven. All the decisions which we make is data-driven. So pretty much every point, we take some data-driven decisions, right? So what is the Uber's data audience? We have thousands of city operation people, which actually runs the Uber, which interacts with the drivers, which interacts with the riders, and try to do lot of data crunching to get to the decisions where they want to go, or what are the promotions they need to do in this particular city, what are the coupons they need to give to the riders. I mean, everything they do. So there are thousands of them, and they actually go and hit our data servers, and then get all the results, and then do all this computation. We have hundreds of data scientists, all these machine learning models, what is the best route, is this a fraudulent activities, everything. These are the people who are actually handling all this. So and there are tens of engineering teams which are making data-driven applications. So these are the people who are actually using our data all the time. So when we start, right, every company starts with a very small footprint on the data world. We have this Kafka, we have this schemaless key value store, and then the RDBMS stores, which consumer all the applications, we talk to them, and then we consume the data. So we're putting it to the S3 in 2014, then doing EMR for some of these, and then and our data warehouse was like Vertica, and all these data operations teams which we talked about were going to the Vertica and handling all this and crunching all this data, right? And the data is At that time, the scale was not that big, so we were happy, right? Okay, we solved the problem, and everybody is so happy. The pain points are simply two, which is scalability. Data grew faster than we expected, right? So the Uber grew so fast, and then the data with that grew so fast. So the basic two problems, which every company, I think, deals with, the scalability and the reliability, because we haven't put the checks in place. Whatever the data is produced, the consumer is producing the same data. So these are the, and that's what we found out too. And then these are the two major issues we found. Then what we did is, we thought there is a Hadoop which will solve our problem. So we installed in our Hadoop cluster in 2015 sometime in the beginning, and this was the scale, right? There was few servers, 100 jobs per day probably. We had some data, very, very less data. No Hive, no Presto, some Spark apps running, right? And that was we started with. This is where we are currently. We have Kafka, all these ingestion will go to the HDFS. HDFS will ingest into the Vertica, and then we have all this Spark, Presto, and Hive directly from HDFS. And then we do all these ETLs and all these CT operations directly from there. And then there are some small use cases which goes directly to the Vertica too, right? So this is the current architecture pretty much. Scale is, we have few thousand servers, 100K jobs per day, many, many petabytes of data, 20K Hive queries per day, 100K Presto queries per day, and few thousand Spark apps per day, right? So this is where we are currently, and we are growing pretty much every second. We've solved few things along the way from the 2014 and 2015 to the 2000 current architecture. The strict schema management, right? So the problem, as I talked about that, our operation folks, right? These are not technical folks, so they just do SQL queries on our data. And for that, the SQL is the key. So, and for SQL, we need strict schema management. And we need strict schemas, and which is backward compatible. So we had to solve this problem. So we solved this problem from the producer side, and we enforced all the strict schemas. We built tool. We have a schema management tool, which we call it heat pipe, and that actually handles all the strict schemas. And if anything breaks, we'll notify as it breaks, and then we solve that issue, right? Along the way, we found Hive, Presto, Spark, because Vertica was not scaling, and scaling Vertica is pretty costly too. So we now depend upon Hive, Presto, and Spark pretty much to solve all these issues. We need to have a scalable ingestion model. We had our own scalable ingestion model, which actually handles all the ingestion from all these data sources, which I talked about, Kafka, schemaless, and the SQL DBs. The reason is you need that system scalable because the data grows exponentially, and then you will hit the wall pretty soon. So you need to do that. We need to think about this from the beginning when we are writing an ingestion pipeline, because it starts very slow and it starts very small, and then it grows very fast. We build all these tools. We need all these Hive registration tool, which actually automatically check, okay, if there is a schema breakage, and then do all the backward compatibility, change the data, and all that stuff. We have this tool called Janus, which is a HTTP endpoint for Hive Presto, where these operation people can go in a UI and then submit a job, and without knowing that if they are submitting into Presto or Hive. We call that UI as a query builder. So yeah, this is where we are. I think we think, okay, we solved the problem. We are happy, we did it. So yeah, so pretty much currently we are growing in this way. We have Hadoop, which can horizontally scale. and we have all these tools which are working well for us. Now what? So we took a step back and we thought, what are we doing in terms of CapEx in the company? And are we really using all the CapEx which we have efficiently, right? So we took a step back and see and analyze what we did. So Hadoop evaluation for Uber is like, in 2014, 15, we have very few nodes. In the end of it, like hundreds of nodes, few petabyte of data. In 2016 is thousands nodes, tens of petabytes of data. And now we have like 5,000 nodes, more than that, and tens of petabytes, hundreds of petabytes of data, right? We have all these many servers, we are horizontally scaling, we have all this nice feature of UFS where we can partition the data, we are happy. But we looked at the graphs. Our cluster utilization is pretty much not that great, right? Memory average utilization and CPU average utilization is pretty much, and the reason is we provision for the peaks. And we think that for this year we'll grow that much, and because of that we need to buy hardware, because this hardware provisioning is pretty much a very hard task where you need to put an order and we buy more hardware and make all these server companies more rich. For the anticipation of that we'll hit the peaks. In Uber case, we actually hit the peaks, but we need to, and this hardware is pretty much ideal for some time, right? Then there is another parallel systems, which is Mesos. And then, because all these services, like I talked about all these dispatch services and how you interact with, when you click on a iPhone, okay, I want to go there, then these dispatch systems. And there's a lot of other system, microservices, right, which runs on Mesos. Mesos is good at running online services. So we have like 2014, no Mesos. In 2015, few nodes. 16, thousands of nodes. 17, tens of thousands of nodes, right? So we have these Mesos in this. This is parallel clusters which we have. But the story is the same, right? And that actually utilization is far less than what we have it in Hadoop. So same problems: over provisioning for peak loads, over capacity for anticipation of the future growths, right? So now the problem is, I'm getting. Is there a power cord? Sorry. Power cord. Can I get a power cord, sir? Hey, thanks, man. Okay, sorry guys. So the story is the same, right? So now what we really need is, we need a better utilization for these tens of thousands of cluster machines, right? We are running at 20% capacity, 20% utilization. Allocation is like 30, 40%. So what we need to do, we need to do something to fix this issue, right? Because this will translate to millions of dollars. And the other problem is, you have these silos, these application silos. You have Hadoop cluster where you are running Hadoop workloads. You're happy. You are in Mesos. You are running a Mesos workloads, and you are happy. But let's say you are hitting a peak on your Hadoop cluster. You need more machines. You can't get it because you need to provision them. Because once you are running in your own data centers, you need them. You need to provision it. In Mesos is totally chilling out, but Hadoop is totally dying. However, you cannot share the resources. So there are these application silos. So pretty much the end goal should be like this, where all these different kind of workloads running together in one cluster. That cluster should run all kind of workloads and should give resources to all kind of workloads when they need it, right? And that pretty much will bring the utilization of each and every machine in your data center high. So what we need is pretty much all the machines together, and we need to have a global view of all the resources, what we have. And then some entity will say, okay, this is the global view of all, this is the whole pool of resources where I can use it, and then take decisions based on what you need. Right now, there are two available resource managers. One is Yarn, another one is Mesos. Being a Yarn committer, I love Yarn. So let's talk about it. What they have, what both are good at. So it's not the whole list. It's a couple of the things which I thought is important for us. So Yarn is a single level scheduler, which is you give all the resources to Yarn, and then resource manager, and then the capacity scheduler or whatever the fare scheduler you use, they take the decision based on that. It's pretty much a single level. Two level scheduler on paper scales better. You have multiple frameworks. In Mesos, there is a resource management layer where you aggregate the resources. That is Mesos. And then you have a frameworks like Marathon, Aurora, and all those frameworks, which you can give offers to those frameworks, and then they will take those offers and then run their jobs. So this is two-level scheduler. On paper, it works. It should be better scalable. It does. But there are other issues with the two-level scheduling, which I'll a little bit talk about it. Both have C group isolation, so container isolation, this is pretty good. CPU memory as a resource in the Yarn. Disk right now it's not there, but Mesos has disk isolation too. And so that is one good thing about that. Yarn is very good at running Hadoop workloads, and Mesos is very good at running longer running services. So, I mean, all of our microservices and all other stateless services runs on Mesos. Yarn has these reservations. Mesos does not have it. That is good for the bad jobs. Yarn has this dominant resource scheduling. Mesos resource scheduling is done by the frameworks. So it's basically the case-on-case basis. And I don't think any of the frameworks on Mesos does have it. So in a nutshell, Yarn is good for Hadoop and bad jobs. Mesos is good for longer running services, right? So what do you do? So the first thing comes into the mind, let's combine them together, right? So we tried, so there is a project called Apache Myriad, and which try to do that in some shape and form. We tried that. So Apache Myriad is pretty much a Mesos framework for Apache Yarn. Mesos manages data center resources. Yarn manages Hadoop workloads. So what pretty much Myriad does is it takes the resources from Mesos and give Yarn, okay, these are your resources, and then what Yarn does is it launches Node Manager on those machines, and then you submit the job as you do for the Hadoop clusters, and then Yarn runs in its own course to talk to the Node Managers, application masters, all that stuff, and then Mesos will handle all other resources. And when you need it, you can go and ask Mesos more resources. On paper, it's simple and clean, and it works. But when we actually go and experimented with it, then we pretty much found that the problems which we are trying to solve is not solved by this. The reason is, so once you have resources, then what it does is, Mesos will give you Yarn resources, and then Yarn will handle those resources. Mesos will not have any say to those resources. So you pretty much doing a partitioning of your resources anyways. So what we actually thought will not do any partitioning of the resources. End of the day, we are actually doing it, right? So this is a problem. This is one basic problem where the application silos thing which we talked about is not going to solve it here. Other issue is oversubscription, right? Any cluster utilization, if you go to any cluster, the utilization increases only when you do oversubscription. When you oversubscribe resources, then only it will be, the utilization will go further, because all the application which runs, they say I want 5 CPU, but end of the day they use probably 1, right? And the 4 CPUs are allocated but not used. So what you do is you oversubscribe your application to the cluster, and then those CPUs you use it, and when the application needs it, you give it back. In this case, if I'm using Myriad, then I can't do that, because Node Manager runs in a Mesos container in the Myriad world. And if I oversubscribe the Yarn, let's say if I want to oversubscribe the Hadoop workload, and if I do that, and it pretty much go and kill the container. The killing the container is just not the application container. It's actually go and kill the Yarn Node Manager container, which pretty much you're losing all the tasks, whatever running on that Node Manager, hampering the SLAs. Similarly, you can't do Mesos oversubscription because Yarn will not let you do that, because it already allocated all those resources. And it will go and kill the node managers too. So this is also, the utilization piece is also not good there. The third thing which we wanted from the system was, we want to globally manage all the resources. We want global scheduling policies. We want global priorities, where I want to say at any single point, I want to use this particular job at higher priority than other jobs. If I'm using 2 schedulers, I can't do that, because they are not talking to each other for priorities. They are not talking to each other how to schedule them. So this problem is also not solved. So pretty much we thought about it, and then we saw, okay, these are the basic issues which we want to solve, and this system is not solving it. We can't do elastic resource management, the utilization is not great, stability is pretty much, it's a very early project, the stability is also not there. And there's a long list of issues which we found over the experiments, right? So we thought it's not a good idea to use that. And it was actually not solving the problem. So what we need is pretty much a unified scheduler which can handle all kind of workloads and do all these scheduling primitives better, which is oversubscription, global policies, priorities, preemptions, and other primitives too, right? So we need one scheduling layer across all workloads. Partitioning resources are not good, so we need to have one pool of resources. We did some experiment, and we found that if we actually schedule everything together, we'll save at least 20 to 30% resources. And if even I think in the paper Borg, Google Borg, they also talk about it. So what we thought, okay, so these are if we want to save 20 to, which is actually a very, very big amount of money which we save, 20 to 30% resources. So that is pretty compelling. And the stability and simplicity wins in production. I mean, all these Myriad stuff where you are one scheduling layer talking to another scheduling layer and launching containers and do all this handshaking, that is, in production environment, debugging any issue will be a nightmare, right? So you don't want to do that. multi-level of resource management and scheduling will not scalable, right? So these are the issues, and then we thought, okay, what we want to do. So these are the high-level characteristics we want to do. We need a global quota management. We need a central scheduling policies. We need oversubscription for both online and batch workloads. Isolation, bin packing, where we can actually use the resources we want to. We need SLA guarantees at the global level, right? And we need to have these scheduling primitives with all these already running jobs, all these already running systems which we have. So pretty much with this unified scheduler, we'll have all these APIs support, Yarn APIs, Aurora APIs, HRM APIs, with all these scheduling primitives, with the job management and Mesos, right? So Mesos, I just put it this way because Mesos is, we are using it as a resource aggregator. It's not as a scheduling layer. We can use Yarn too for that, but the Yarn source code is pretty much combined with capacity scheduling and resource management. So resource management, we wanted, so if you think about the Yarn, we wanted to remove resource management from a resource manager. So that's pretty much, so Mesos, it does it pretty well. So Mesos is just a resource manager which manages the resources, and you tell them, okay, go and launch this container. It will go and launch it for you. But all the decisions is made in this scheduling layer. That's what we want to do. So we compared all these scheduler, what each scheduler does right now, and what are their availability. So we have this, right? So we compared this Google Borg. There's Yarn, Mesos, and the Kubernetes, right? And these are the things which we want to do, application workflow management. Borg has something called controller jobs, which does that, where you want a specific application to manage its own workflows. Job task lifecycle, task placement, task preemption, resource allocation is done on the Borg master. And the task execution happens at the Borglet level. Yarn, job task lifecycle and application workflow happens at the application master level. Rest of the things happens at the resource management layer, and the task execution happens at the node manager level. For Mesos, these are the frameworks which does everything. So that's the reason, right? So see this, all these things, task preemption, job, task lifecycle, application workflow, everything is done at the framework level, which is other than Mesos, right? And Mesos only handles the resource allocation piece and launching container, task execution piece. So that's the simple abstraction you can get from Mesos. So you don't need anything else from, so Mesos does not do anything else other than these two. We have Kubernetes. Kubernetes has this kube controller, and then kube scheduler do all these things, and then kubelet will do task execution. We looked at the Kubernetes. The problem with the Kubernetes right now is it does not have all this elastic resource management piece. It does not have global priorities, all this stuff. And you cannot share the resources. And in the multi-tenant system, you need all that. And I think from the latest benchmark results, we found out that there is like only 2,000 nodes somewhere is running, not more than that. Borg is not open source, we cannot use it. Mesos, okay, so Yarn, so the reason we didn't go through Yarn because it does not run for the online services very well right now. I think they're adding the support for that. We need the GPUs supports, which they're adding it, but right now it's not there. And the other things, service discovery and all that stuff. And we need the throughput from the system is like thousands of tasks per second, which is not there in Yarn right now. So we looked at that, and then we thought, okay, let's write something which is the first option for all the engineers anyways, so which can solve our problems. So we are writing something called Peloton. It's pretty similar to Borg in all these primitives. We have this controller job, we have all this lifecycle management, and we are using Mesos underneath just for resource aggregation and task execution. We started to hit the limits on the Mesos. By that, if you want, we can remove Mesos later. But right now, this is the easiest option for us to go and use that to run our workloads. So this is a little bit talk about this here. So the Peloton architecture, we remove, so think about the resource manager piece in Yarn. We change it to multiple components. One is the job manager component. There is another resource manager component, placement engine, and the host manager. So the job manager only handles the job and task lifecycle. The resource management piece handles all these admission control. What is the elasticity in the resources? Which task to be scheduled, which not to be scheduled? What is the preemption? How to do overcommit? How to do oversubscription? So these things have been done in resource manager. Then you have placement engine. Placement engine is pretty much a stateless services, which what it does is, based on the workload, it actually matches the resources and launch them, right? So you can add your own placement engine. So what placement engine does is, let's say for batch, there's a paper called Power of Two Choices, right? You just want to use that and just run your batch workloads. Any coming resources, you can just match it and then run it. But if you want to run MySQL or Cassandra on top of it, then you need to have affinity and anti-affinity. You need to have placement decisions which will go and see which this particular SQL daemon or Cassandra daemon or whatever, Oracle daemon will go and we should run on that particular node or not, right? So we have these multiple placement engines for each kind of workloads. We have this host manager, which is actually an abstraction on top of Mesos. So what we can do pretty much, we have multiple, let's say if you, so right now, one Mesos cluster, we can have multiple of these Mesos cluster underneath to run on Peloton. And we can aggregate all these resources together and then have a same scheduling policies, same elasticity, same resource sharing for all these Mesos clusters. We have all these API support, auth, and we have the basic thing we have is Cassandra. So we are using Cassandra for our stateful. If we lose our state, we are using Zookeeper. So all these, the good part of these services, these are horizontally scalable. So we have multiple of job managers running, which can handle multiple of users' requests. We have multiple resource manager running. We have multiple of placement engines running, and multiple of host managers. So you think about Yarn in active. You have multiple of it and running everything together. And we are doing leader election through Zookeeper for all these services. And they do discovery also. These are the initial results. We have like 5K tasks per job and 100K tasks per job. And Aurora is pretty much taking 300 minutes. And our Peloton is in few minutes we are finishing that. We haven't done it yet with the Yarn, but we probably will do it very soon. What we have done so far, we have batch workload support, Spark support, we have GPU support, we have distributed TensorFlow support, we have gang scheduling where you can do all this distributed TensorFlow needs state. Work in progress, we'll work on Yarn APIs, stateful and stateless services, and separate placement engine for stateful and stateless. So that's in progress. And we are building this control panel where the Peloton cluster will deploy a Peloton, right? So you will have one solution which can manage itself as well as all the services. So Peloton timelines, we have beta released. Production, we are going early Q3. And probably we are going to open source in Q3, Q4 timeframe. This is the Peloton team. And yes, we are hiring. So if you guys want to know more information, you can talk to me about it. Questions? Sure.
1 second.
Can you take the mic?
Yeah, my first question is, how was the rollout? I mean, do you keep the old resource scheduler, and then this new one, and you roll out maybe like a 500 nodes or something like that? And the second question is, how does the new scheduler handle like small jobs, especially Hive queries, small jobs? How do you handle that?
So for the small jobs, so I'll take the second question first. For the small jobs, so the two things, it will be used what are the scheduling policy you're using for your scheduling the resources to each job, right? And there are multiple scheduling policies you can configure. You can say first in, first out, or you can say my small job, this particular resource pool or the queue needs fair share of resources. So if you configured your resource pool as a fair share, then each and every small job will get their own share. And for the rollout, so we are supporting the APIs, the Yarn APIs and the Aurora APIs, and we have a separate cluster for that. And then we will migrating each services to that new cluster.
In the first question, wouldn't the first scheduler, your new schedule, have a snapshot of what is available at the beginning in order to provide the free space or slots for your jobs?
Sorry, which one? This is the one? This is the question? I didn't get your question, sorry.
I guess my question is, how did the first scheduler, your new scheduler knows about which is the free space that needs to provide for your jobs?
So the new scheduler has the global view of all the resources. So once it has when it knows what is my demand, what are my resources availability, and what is already running, then it can take a decision where to run, right? And then it can use those free resources for what kind of workload. So let's say if you're running a IO intensive job on particular host, then you can say, I don't want to run another IO intensive job, or you can have an anti-affinity constraint where you don't want to run it there. So it can take all these decisions in the placement engine.
Are your batch and real-time or online workloads scaling up and down at different times? Because otherwise you're just going to over-provision both of them, right?
Yes. So most of the time, your peaks and so there is a policy where you need to buy resources from this system that, okay, I want to buy P0 resources, then your reservation is that much. And if you're going to go over your oversubscription on that, then we will allow to do that. However, you will be charged for less. And then the SLA guarantees will not be there. So the SLA guarantees will be on the resources which you buy from the global pool. And if you don't buy those resources, then that will be on the best effort basis, right? So we'll do a reservation and we'll give the guarantee of the resources on the reservation. And that reservation people has to, or the teams or the organizations has to buy.
Yeah, so I have a question regarding, so if you have
few jobs which require special hardware like GPUs. And since this has a global view, how do you distinguish that? And how does application provide you that information that this particular application will need special hardware so that it can run only on specific nodes, not on just any node?
So every application has a resource vector, right? When you submit an application, you tell us, okay, this is the resource vector we need. This is this many CPU, this much memory, this much GPU. So there is a resource vector. You need to specify for every job. I mean, right now, you see if when you submit a MapReduce job, you don't do it, but application master do it for you, right? So similarly, you need to specify that application, so resource vector, and then this global, the Peloton knows, okay, this is the resources they need, and first of all, are they allowed to run on it? If yes, then how much? And then we know, as we know the whole cluster, we know where to run it, based on your priorities and SLAs.
So you initially mentioned that there was a separate Mesos cluster. Can you give examples like what kind of jobs were running on that cluster?
So the Mesos, all these online services, right? All these microservices, all these dispatch, I mean, all these stateless services right now runs on Mesos.
We need to wrap it up.
All right, I will be here, and so if you guys have any more questions, you can.